Okay, so in this lesson we will talk about the notion of frequency, but in a deeper way. Okay, because in the previous lesson we have talked about it. What's the shape of this frequency pattern in geometry? But in this lesson we will continue with the derivation of this term in an algebraic way. Okay, because in the previous lesson we show the Euler identity formula, right? But it's a geometrical representation, not the algebraic one. But how is the reflection of this geometry into the algebraic one, or the number one, or the function one? Okay, this is the topic of this lesson. Okay, and so as we know, we can define the dynamicity of system or thing using what? Imaginary component, right? And so we can define also a signal in here. Okay. And so now we need to focus on solution between the algebraic, geometrical or geometric representation of frequency. Okay, this is our basic form to our topic. Okay, and so just remember the last lesson we draw the real and imaginary axis, right? If you have a perfect sphere or circle in here, just like this one, and then we can define the polar coordinates, right, with the radius of the r. Okay, and so we have also a degree in here, and then we can generate to use this r value to build the imaginary and the real parts. Okay, but it's the complete absolute values of these terms. And so how can we derive this formula? This geometrical shape is coming from the e over I dot pi plus 1 is equal to 0. This is the Euler identity. Okay, and so this is the algebraic function to build this circle in here. Okay, and so this is the identical with this geometry. And so just remember the last lesson. If the r is equal to the c or any other constant, and we can transfer the real energy to the imaginary one. Okay, we can transfer it, and also we can take the imaginary energy to the real one to observe it. But in real life we can only see the real parts. We cannot see that, but by using the math and this geometrical shape, we can sense it, we can formulate it. Okay, in the math, but in real life we cannot see this pattern. Okay, and so if this is the constant, and so no energy change in this system, which is based on based on the derivation of the imaginary axis, right? Because the I or J part of the math is built with the with the no change of this radius or the hypotenuse, right? This is the proof of these terms. And so, how can we utilize this geometry in order to build the frequency pattern? Just see that we know also that I over E over I 0, which is equal to the what? The 1. Exponential I times pi divided by 2, which is equal to the what? The I, right? And I 2 pi 2 is equal to the what? Minus 1, right? And so exponential over I 3 pi divided by 2 is equal to what? Minus I. And so exponential I 2 pi is equal to the what? 1. Okay? Just like this, that 1 I minus 1 and minus I, and at this case we return to the same point in here. Okay? And so what about this one? This is 1, it's equal to this one, right? And so what about the I 5 pi divided by 2, which is equal to the what? I. And exponential I 3 pi is equal to the what? Minus 1, right? And so it goes on at this case. And so we have this domain as a periodical one, but with basic definition of this, that if we take over part or increase the over part in here, and so we return to the same point. This is a pattern to define these nominations, okay? And so this geometrical representation can be defined or state with using with the what? With this pattern. And so we call it to what? The frequency, right? At each case, if we increase the over part 1, 2, 3, 4, and then we will get the what? The same point. This is the shape of the frequency. This is the representation of the algebraic one for the frequency patterns. Okay? And so, but this pattern is a perfect one. What's the meaning of the perfect in here? What's the meaning of this? Why is this perfect? Yes, the hypotenuse is not changed in here, and so we have no energy dissipation in here. And we can convert the time to the what? To the frequency one, or we can convert the frequency to the time with no dissipations. But what if we can define a new pattern just like this one? Real, imaginary, right? And so we have 3 points or 4 points in here, just like this one. And so we have a square form with the 45-degree tangential rate, right? And so we have the 1, it's the j, and minus 1 and minus j, right? And so in this case we cannot complete this task because the hypotenuse is always changed in here. And so how can we model this term in the what? In the mathematical way. Because in real life application, for example, if you want to measure the signal called the xt, we cannot take the ideal signal, there always be a what? A noise, or some unwanted pattern, or the some another else, right? And so this form is the basic representation of the one important signal. What is that? We will always use this signal in real life. What is it? If you don't have any guess, we can formulate this pattern in here, just like this one. Real and imaginary, and we have this square form in here, just like this one, and so 1 j minus 1 and minus j. Okay, and so this is the formula of the what? This term. If you want to formulate this pattern in here, we can define the y1. This is the signal, what the district signal, and so 2 pi times pi divided by 2 minus t, d is a time, and plus 2 divided by pi t j. This is the exact formula for this pattern, because we goes to what? From the real to the what? To the imaginary one. And so this quantity what? Reflect this signal. And the other signal is that the y2, which is the 2-second region, which is given in here, 2 divided by pi and pi divided by 2t plus 2 divided by pi and pi minus t dot j. And so the another signal is the y3. y3 is equal to what? 2 divided by pi t minus 3 pi divided by 2 plus 2 divided by pi minus t dot j. Okay, and so y4 is equal to the what? The another term, 2 divided by pi and t minus 3 pi divided by 2 plus 2 divided by pi t minus 2 pi dot j. Okay, and so in order to create this pattern, we use, or we must use, the 4 distinct functions in order to do that. Okay, but this problem, 4 different functions should be used to define this pattern. And so in real life we can see this signal just like this one. For example, it's the yt signal and the t in here, and so we have the 1 and 0 and minus 1, and then we have simple period in here, just like this one, pi divided by 2 pi and 3 pi 2 and 2 pi, right? This is the formulation of these terms. And so this form gives us to what? To this signal. And so this is a triangle signal, right? This is the definition of this term. And so at each case we repeat to what? To one period of this signal, just like this one. right? This is the period. But in this form, we know this form. We build it. But how can we define this pattern in a way of the what for a given xt signal? Because in this signal, we define y1, y2, y3, and y4. But in real life, we take a measurement from the what? Yt, right? And so this signal could be just like that. And so how can we obtain the frequency pattern of this term in real life? Because in real life, we don't have this kind of signal. This is also a perfect signal, but the energy is changed in this signal. But in real life, always we take a measurement just like this one. And so we need to build a form to what? To extract the specific frequency of these terms based on these informations, right? See, this is the energy change form in here, but it's also perfect, nearly perfect in here. But in real life, we always deal with what? With this kind of signal, right? How can we build this form? So, any question about that? You get the notion of this term? Because if we have a signal as a triangle or another else, and then we need to apply, or we need to create a common mode to what? To represent the frequency values. Because in real life application, we will have this kind of signal with the noise values, right? And so we need to extract the information from this second signal, right? But how? How we can do that? Any question? Do you understand the problem in here? Because we can build this signal based on the what? The Euler identity or the any other algorithm or the pattern in here. We can generate it. But if we have the measured values in here with the noise or some unknown pattern, how can we define or how can we obtain the specific frequency value from this signal? This is our problem. So, problem is that how can we define periodical signal to combine every signal? This is our problem. Because if you want to measure the frequency, and so the measured signal yt or xt can be contained or created with this signal. Otherwise, we cannot build that. We cannot analyze that. Just remember the Fourier series, right? We can define a function or any function, any signal based on the what? The infinite series of the what? The sinus and cosinus, right? And so, at each signal, we have one cosinus and one sinus, or infinite, right? But we don't know the frequency values of these terms, right? In another form, yt is a combination of the what? The ak sin 2 pi f1 t plus vk cosinus 2 pi f2 t, right? But this cosinus and sinus may be ck cosinus 2 pi f3 t plus plus plus. And so we can define any signal based on this information. But how can we obtain frequency value, right? these are problem. Because if you have signal with the noise or the unknown pattern, thus always contains the what to this pattern. We know it. We know that. Okay? Yes. 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 Because every signal in the universe, or the signal and system, or in the imaginary world, should be built with the what? The infinite series of sinus and cosinus. We know it. Because everything has a vibration in signal or in unknown seas, right? And so we need to use this idea based on these informations. Okay? And so the solution can be given by with the what? Suppose that Bix is our model. Okay? Bix, B over Ix, we suppose that these are the model to contain, to define the everything for a given signal. Okay? And then we can use this signal just like this one. We can expand the Taylor form of this term in here, just like this one. 1 plus I ln B x plus I square times ln B square divided by 2 factorial, right? And so this is also 1 factorial, and also plus I over 3 and ln B over 3 divided by 3 factorial plus blah blah blah. Okay? We can expand it, right? And so just remember that we have an x value in here, and so we can build the what? The variable. Variable to what? To root number, right? Because we can choose the what? The x is equal to the what? The 5 or 10. We can generate the 10 distinct features of this term, or we can define the variable features based on this term. But I is a special operation in here, right? I gives us to what? Periodicity, right? And so this is the first term, this is the second term, third term, and fourth term. After that we have I4, I5, I6 and I7, right? And so these are also a periodic function. If we expand this form in the Taylor expansion, and then we can reach the what? In the first place we have 1 line, in the second case 2 line, in the third case we have 3 line and 4 line and 5 line, and after that we reach the what? The Euler identity at each iteration, right? And so the I gives us the periodicity. X is a different feature. And so if we expand this form into the Taylor one, and so we can have the infinite root pattern in here. Okay? And so how about Ix, if we used in this case, we can build the any function using what? Infinite series operation, because the Ix contains the what? The sinus and cosinus, right? If we take an expansion form of these terms, and then we can change this b value with what? With the e, and then we can build it, because in the E, at each case, just remember that, in this case, I, E, X, at each case, we can take a derivative values of this term, dx I x is equal to what? I x, right? And so dx square, and so I square I ex, and so I3 I ex, I4 I ex, right? This is the basic pattern that gives us the returning to the what itself, and then we just take the only the what, this pattern, I over 1, I over 2, I over 3, I over 4, I over 5, and blah blah blah, but with a basic difference in here, just like this one, E I T, in this case we use the what, the time in this pattern, because time always increased in linear one, and so we can build this one and I1 t plus I2 factorial t square plus I over 3 factorial plus I4 t4 divided by 4 factorial plus blah blah blah. Okay, and so the rest of them are t, is a function of the higher order complex, right? And so we have this pattern in here. This is the periodic one, right? And so at each case, just see that we have a circle in here, just like this one, real and imaginary one. And so we have T0, T1, T2, T3, T4, T5, T6, T7, T8, and blah blah blah, and goes on. That at each case we increase the distinct feature of this term, but this is periodic one, right? Because at each iteration we can take this notion based on the what, the EIT, right? And so this is the note 1, and also we have a note 2. What about we use this pattern E over 2 pi a t in this case? If this is the case, and so if we have this pattern in here, just like this one, if we are using the a is equal to the 1, we can take the 1 rotation, right? At each case for a equal 1. But if we have a is 2, and then we can take the what, or a is 3, we can circle to the what, the 3 round at display, right? And so 2 pi is important parameter for these things, because if we select the 2 pi in the over term, and then we can build the one Euler identity circle in here, just like this one. And so at each case we have a t in here, and so t is also another feature in here. For example, t is beginning with the 0 to t infinity, and so how much or how many roots are created based on this form? How many roots? If the t goes to infinity, and so we have the infinite number of features in here. But this is not useful, because if we have an infinite number of features, and then we cannot model it, right? Because we cannot measure it. But thanks to the Euler identity formula, we can build a periodicity in here. Just like this one, right? And so, if we take a new coefficients in here, just like this one, and then we can build the E2 dot pi dot a dot t is equal to what? The 1 plus 2 pi a dot I t plus 2 pi a I square t square 2 factorial 2 pi I a e I over 3 and t over 3 factorial and blah blah blah. Okay, and so we have one pattern in here, 2, 3 and 4, right? And so at each case we returns to the what? To the same point, imaginary and real one. Okay, and so how about this? In this case we have the 1, and so in here we have 2pa, and so in here 2pa square, and here 2pa over 3, 2pa 4, 2pa 5, and blah blah blah. At each period we return to the same point, but with the what? With the different coefficients of these terms. Okay, this is a frequency, but with a different coefficients, right? At each case we can build this pattern in here. This is the periodicity, and so at each case we can increase the number of the what in these terms. Okay, and so if we are using the a is equal to the 1, at each case we can goes to the what in these coefficients to the infinity, right? See that if the a is 1, and so we can take the 2 pi pattern in here, but if the a is the 100, and then we can get to the what? To the infinity in these coefficients, right? And so at each case we highest value, and at one point we have the 0 value or the some constant value, which is the 1. Otherwise this integral form is always with the what? Going to infinity, right? It's important to understand these things. If you have any question, please ask me. At each case this Taylor expansion increases, right? 1, 2, 3, 4, and so this value is always going to what? At each frequency to the what? To the infinity, because the over term is always increased in here. And so this form creates the infinite values in this form, but at one point if the a is equal to the 1, and so this point we have a minimum value. Okay, please ask me. It's a highly abstract concept. Do you get it? Okay, in order to understand this term, just see that in this case 2pa and 2pa square 2pa 3, and so it always goes to the what? The infinite value, right? At each case, and so t is going to what? Infinity, right? It's always increased, and so this coefficient is the Taylor coefficients goes to what? To infinity, right? If the t is increased, right? You know it. Okay, and so if we have the signal as equal to the a to the 1 in here, and then this a creates the same pattern just like this one. If we have the Euler identity formula, with based on what the A1, and so this signal is always in the Taylor expansion form, increases just like this one, okay? But with one pattern is exactly match this pattern in here, okay? Otherwise it goes to what? It's going to the infinity and always is increased in here, okay? And so this pattern matching at this time is the what is the minimum point of this term. And so if the A is 1 in here with this pattern, and so we have a minimum in here. Otherwise we goes to infinity, okay? In this case. You get it? How we can use the Taylor coefficients in here? The Taylor coefficients gives us to what? If we have the one pattern to match these coefficients, and so this is a minimum point at this time. Otherwise we goes to infinity, right? Okay. And so as a result, if we have this notion and then the I is the imaginary number with power form, creates periodicity, right? I0, I1, I2, I3, and I4, I5, I6, and I7. Okay? One period, two period. Secondly, each variable power form is related to one term, like 1 plus it plus I square t square plus I3 t3 plus I4 t4 blah blah blah. Okay, and so we have the periodic coefficients in here, just like this one. Okay, and so this builds to the what? Periodicity at the power form. And after that, in this case, this is the equation coefficients with the what? With some pattern S, I0, I1, I2, and I3. And so this S defines the what? The every period in here. For example, it's the K. And so we can build the YT signal in here with this periodicity, right? Because it contains the what? The specific frequency at this case. And so we can also write that then if we take coefficients 2 pi, we have E over 2 pi dot I dot t gives us the 1 Hertz value, because it's the one rotation in here, right? This is the basis of the 1 Hertz values in here. This 1 Hertz, because it's the 2 pi is equal to the what? The 1 Hertz, and then we can say that this t is increased in the what? In the 1 second, and so this is equal to the 1, and then this returns to a 2 pi dot I, right? Because this is the 2 pi in the polar coordinates, and then this I removes to what? Any other term. And after that we can conclude that if this is the time, and then we can build the what? The E over 2 pi ft, and so this must be equal to the f Hertz, right? if we can use the f is equal to the 1, and so 1/3. If we use the f is equal to the what? 10, and so this is equal to the what? 10/3, right? Okay. And so this is the second rule. Just remember that if we have a minimum value at one point, for example, f is equal to the 1, and so we have a minimum value because we have the exact match between the what? The Euler identity formula, right? And so these are the formula 2 pi ft, right? And so if this is the formula, and then we can build the what? The another formula minus 2 pi ft I. If we are using the minus term in here, and so this is going to what? This one, right? No, A is considered as f. Yes, f, and it's the frequency pattern in algebraic form, right? And so if we use f as the 1, and so it's the 1/3, right? Because it completes the one spherical or circle coordinates of the what? The Euler identity, okay? And so if we choose the f is equal to the 10, and so we can create a 10 Hertz variation in here. But if we choose this term is always going to what? The infinity. But if we use the inverse term of this term in here, just like this one, and so at one point we have the maximum value, infinity value, and the other part is the what? The 0. And so this is the maximum value, right? And then if this is the case, and if we have any arbitrary signal, we can multiply this signal with this formation, right? If we multiply this term, and so at each case we can compare the R signal in real life xt, and this is the what? The 1, j minus 1 and minus j, and so we can convolve it, we can compare it, we can match it. And so if we have a specific frequency for this signal, and so this signal is matched with the what? With this Euler identity formula, right? We can match it because we prove it in here. And so if we have specific frequency in here, and then we can take or collect the whole the terms in here, just like this one, okay? And then if this is the case, we can conclude that we have an integral in here, minus infinity plus infinity xt e 2 pi ft I dt gives us the x 2 pi f, which is the definition of the what? What is this? Fourier transform, right? And so what is the Fourier transform? Fourier transform means that if we select the frequency pattern in here, just like this one, and so we can maximize the signal at each specific frequency if we contain it, okay? And so this transform is based on the what? The Euler identity, but we should use the what? The minus form of this term. Why? Yes, and so this point represents to what? The specific frequency. And so this transform gives us to what? To our pattern, our frequency. And so this is dt at integral term. Why? Because we have the infinite root in here. minus infinite and plus infinite, right? And so these have the independent or the infinite distinct feature is collected in here, but some parts is to build or creates the what? The infinite value, the higher value. The rest of them returns to the what? The zero in this case, right? And so this is the case if we take or apply this integral with these coefficients, and then we can what? We can obtain our frequency pattern based on this information. Because just see that if we have this information in here, e I 2 pi f t, and so if we expand this form in here with the Taylor coefficient, just like this one, xt times 1 plus 2 pi f, right? I t plus 2 pi f I square t square plus 2 p f I over 3 factorial plus blah blah blah. Okay, and so at each case we have specific frequency, right? This is the f1, for example, and so we have always the f2 plus 1 2p f2 I t plus 2p f2 I square, this one, and 2p f3 2 I over 3 t over 3 factorial blah blah blah. Okay, at each case this xt is going to what? The coefficient of this term, right? We multiply at each time this coefficient, just like this one, xt plus 2 pi f1 xt I plus t 2 pi f1 xt I t square 2 factorial 2 pi f1 and xt I over 3 t over 3 factorial blah blah blah. Okay, and so if this is the R frequency which is given in here, and so this yields us to what? To R infinite value, and R to what? Infinite value. R to what? The infinite value. Okay, because we have this pattern here, and so if the f1 is exact match with this frequency, and so this pattern is to what? Is multiplied with the another one, and so at each iteration this goes to what? The infinite value. But if you don't have any frequency components, this Taylor coefficient goes to what? The 0. And so we can obtain the what? The f and magnitude of the signal, just like this one, yt, in Fourier transform, just like this one, right? For example, 100 Hertz. And so what is this point? This point directly relates to the Taylor coefficients. Okay? Any question?